All right, welcome in Calc 3. It's Tuesday, October 5th, and we are at the start of week 8, midterm week. Yeah, and speaking of midterm, you don't really have a midterm, but you do have an exam this week. Chapter 12 has opened. You can start taking that. There's a download part and one that you have to submit, and then there's an online portion, similar in format to the Chapter 11 test was just a couple weeks ago. Yeah, and yeah, Chapter 12 was real fast. It was 5 sections. And there's actually 5 videos from class on those because I was able to do 1 section per video in chapter 12. So be sure that you're reviewing for that if you're watching this before you've taken your test and all that stuff. So hang in there and hope you have a good week preparing for that and taking care of that. But on to content. So once you're ready for chapter 13, let's get started here. Chapter 13 really starts the idea of multivariable calculus. Multivariable calculus. So 13.1 is all about the introduction to functions of several variables, right? We are used to functions of a single variable, f of x, right? But now we're going to start talking about what it means for a function to have multiple variables. So intro to functions of several variables. I'm going to already apologize for my dog. I can see she's looking outside, and I'm sure she'll bark at any time here. So I apologize if she ends up doing that. TA, be quiet. We're in class. Yeah. Okay. Anyway, so functions of several variables. Now, in some sense, you have already worked with functions of several variables. I mean, in Calc 2, we talk about work done by a force, right? And so that's a formula that's work equals force times displacement. Yeah. And what I can think about is that work depends on 2 things, right? Not just a single thing, but 2 things. It depends on the force, and it depends on the distance or displacement caused by that force, yeah? And so I could think of this as a function of 2 variables. In other words, I can calculate the work based off of F and D. In other words, it's a function, W is a function of F and D. It's a multivariable function. Instead of just F of X, or a function of a single variable, we have now a function of 2 variables. One way to think about it, if you're like a computer programmer, right, think of it as like you have 2 inputs that it accepts, and this function is then going to calculate a single output. Yeah? You have the volume of a circular cylinder, right? That's pi r squared h, right? So again, volume here is a function of 2 variables, radius and height. Now, you've worked with these and even done calculus with these, but it was always some simplification that didn't allow r and h to be independent of one another. So you could still use your single variable calculus in Calc 1. What I mean by that is here we can say let the radius be whatever, let the h be whatever, and maybe they're changing on their own, right? Maybe the radius is changing and the height is changing. Your problems from Calc 1 that did problems like this would say always something like, assume the height is 1/2 the radius, right? Or they'd throw something in where you could make the height now not really matter, where it was just a function of r. So then you could get a single variable and work with it, right? Here, we don't want to do that. We want to truly treat radius and height as independent variables that have no connection necessarily to one another, but when connected in this way, connect to volume, right? So in other words, I want a function of 2 variables. The volume is a function of radius and height, r and h. And of course, the volume of a box, length, width, height, right? That's actually a function of 3 variables, isn't it? It's a function of L, W, and H, right? And so this is expecting 3 inputs and then calculated to get a single output, right? So this is what we mean by a multivariable function. So here's the generic notation that we're going to use. We're going to call the output of these functions generically z values, and we can say that that equals some f of x and y, right? So in general, we can say z equals f of x, y, right? Function of some of 2 variables, x and y. Now, sometimes you're given a formula, how to calculate with that, right? And so you can say this is, let's say the output is x squared plus xy. Right, so it would take whatever x value you gave it, whatever y value you gave it, plug it in, calculate, and then output a value. that would be a function of two variables. Why is it a function? Because notice that you only get one result for every pair of inputs, right? So you're not going to get like, this equaling 10 and 20 at the same time for the same input, right? One input gives you exactly one output, right? You can have functions of 3 variables, let's say. When we do that, we usually call the input variables x, y, and z, and the output variable then is w, right? That's generically how we usually label it. And just to say, for an example, you might be given a formula. Maybe this is x plus 2y minus 3z. Okay? So bottom line, we have now the idea of a function of 2 variables, 2 inputs, then giving it a single output, or 3 inputs, giving a single output. Yeah. One way we can think of that pictorially is the following, right? In Calc 1, you had y equals f of x, right? So you would have like the domain space, if you will. This is the x-axis. You would pick a number over here, and you would follow a rule, plug it into f, and then it would output a number over here, right? In the y space, if you will. Yeah. Now we're used to graphing these functions like this, right? So I would take this y-axis usually and put it here, and then I would have the graph of a function, right? But I could think of this as an one-dimensional input space, taking one number, a single number, just in the one dimension, and then plugging it in, calculating, and getting a value over here, which is just a single number. Yeah. Now the case being, in Calc 3 right now, here I could take, instead of a single number, I'm going to take a point, say some x comma y. That gets thrown into a function of 2 variables. I calculate using the x and the y, and then the output is a number on the z-axis. You see that? So you can see that in the sense here that the input is already 2-dimensional. In other words, there's 2 dimensions to it. There's an x dimension and a y dimension. There's 2. See, don't overthink dimension in this case. I'm not necessarily thinking spatial, even though I can think of it spatially. I'm thinking of this as just a list of things I'm keeping track of. I'm keeping track of an x number and a y number. And so that's 2-dimensional thinking, right? Thinking of 2 things associated. Plug those 2 things in, get a calculation, and you're going to get a number as an output. Right? So 2-dimensional input gives me a 1-dimensional output. If I was to graph this function, do you see how the graph would have to be 3-dimensional? Because I would have to show you my 2-dimensional input space, a plane, and then show you somehow a 1-dimensional space. Well, that's pretty easy to do. Here's my input space being a plane, and here's my z-axis. I can just put it straight up like that, and now I have a 3D sort of space that I'm working with. So the graph of the function z equals f of xy is actually going to be a 3-dimensional picture. 2 for the inputs and 1 for the output. Notice for Calc 1, the pictures were 2-dimensional. Why? Because the input was 1-dimensional and the output was 1-dimensional. This does bring us a problem of visualization here if I go up to the next case, doesn't it? Because look at this. For this case, I have a point that's already 3-dimensional. It has an x-coordinate, a y-coordinate, and a z-coordinate. Then I map that over here via w equals f of x, y, z. So this maps to a single number. So the output space is still 1-dimensional. This is the w-axis. But do you see how I would have trouble graphing in the traditional sense? Because the graph of this function would have to be some 4-dimensional picture, right? Because my input is already 3-dimensional, and then I have to tack on a 4th dimension that's not a combination of the dimensions that I already have. Do you see that? And I can't visualize that. I don't know how to do that as a human being. I don't know what that looks like, right? So now we have to get into other tricks on how to represent 4-dimensional graphs, right? Sometimes you could say, okay, here's the input represented by the XYZ, and now a color, strength, or gradient represents the 4th dimension, right? Or you can maybe say that time is that fourth dimension, right? If you don't want to think about that. And so this is a three-dimensional picture in motion throughout time, right? Sometimes you hear that. So anyway, there comes a point where I can no longer visualize these functions of multivariable functions traditionally in the way that I'm used to in Calc 1 and Calc 3 here for that, right? So anyway, let's get into what we can talk about with functions. Usually one of the first things we talk about with a function is what are the valid inputs? In other words, what is the domain of our function, right? So let's go ahead and now start talking about how I can think about that. What's the domain of functions? Well, suppose I have this function here. I have f of xy equaling this formula, the square root of x squared plus y squared minus 9, all divided by x. Okay? Now, here's one thing we have to think about right away. In Calc 1, when we asked for the domain of a function, well, the input space was a single axis, right? The x-axis. I pulled a single number, plugged it in, and then got a single number as output, right? So the domain was a space, some subspace of a one-dimensional thing. So it was an interval, right? It was like, oh, values between here and here are okay to plug in, but over here, not able to plug in, not defined or whatever, right? So in Calc 1, our domains were one-dimensional, right? They were intervals, right? Here I have an issue. My input space is two-dimensional. So if I demonstrate or show you the domain of this, right, the domain necessarily now is a two-dimensional picture. So it's not appropriate to use an interval. I can't say, oh, this is values for 0 to infinity. Well, first off, what values? Are you talking about x values? Are you talking about y values? See, there's two values you have to pay attention to now, right? And so this domain of a function of two variables is necessarily a two-dimensional idea, right? Let me show you how we can attack such a problem here, right? You're doing the same sorts of things that you did for single variable. You're asking, well, what's valid to plug in? What's allowed to be plugged in? For instance here, right? Ooh, that was a big boom. I'm surprised my dog did not bark. That scared me. You might have seen me jump. That's so funny. Anyway, so what we have going on here is the same sorts of things that we do for Calc 1. You're looking for places or numbers that will divide by 0, right? Or things under the square root that are not defined, yeah? So notice right away, I notice here, x cannot be 0, because if x was 0, I would be dividing by 0. So let's note that right away. Note that x cannot be 0, right? Because then I would be dividing by 0. Then we also have the following restriction here. Since this is underneath a square root, this has to be greater or equal to 0, because you can only allow positive or 0 numbers underneath a square root, right? So we have another option too. We have another problem. X can't be 0, and we have to guarantee that x squared plus y squared minus 9 is greater than or equal to 0. Yeah? Okay. So that is a requirement. Solving for this gives me this relationship. Adding 9 to both sides. This is that x squared plus y squared has to be greater than or equal to 9. Now, here's my domain. So I could say that the following is the domain. So I can say the domain is, and you can use a set notation. And now you say all xy pairs, right? Because I'm inputting two numbers, x and y. So I write that as an ordered pair. And I can say such that either a line or colon, whatever you use there is fine. And then tell the conditions that have to happen. So say that x cannot be 0 and x squared plus y squared has to be greater than or equal to 9. And that is a description of the domain, right? As long as your x and y obey these rules, then you're in the club. You are in the domain and you're valid to be plugged in, right? If one of these rules is broken, then it's not in the domain. It's not possible to plug that in and get something, right? For instance, if x was 0, well, I would be dividing by 0. That's a problem. If I got that x and y were 1, for instance, if these were both 1, notice I would have 1 squared plus 1 squared minus 9. Now I have a negative under the square root. No good. Right? So this does describe the points that are allowed and not allowed. But it's not very visual, right? It's not very, I don't see what this looks like, right? I have rules that I have to follow, and if the XY pair follows these rules, then it's in. Let's see if we can make a picture out of this, right? What would this look like, right? So what I can do is try to draw a picture of what this would look like. It is a two-dimensional picture, so I'm going to draw an x-axis and a y-axis. And let's think about what this means. X squared plus y squared greater than or equal to 9. Well, wait a minute. X squared plus y squared equal to 9 is a circle centered at the origin with radius 3, right? And that's okay, right? Because if it's equal to 9, then it's in the domain. That's good. So I do know this has something to do with the circle centered at 0, right? With a radius 3. Yeah. Now, also, x better not be 0. So let's take care of that first. X not being 0 means you cannot be on the y-axis. So one way to indicate that on paper, when you're doing this by hand, if you are, you just dash that line. And that communicates that you are not allowed to pick values on the y-axis. Okay, so that's out. This circle is okay here until, oh, look, this circle is here. Let me put a hole there. Right, because it's not the circle's fault, it's this line's fault, right? But this circle is okay. This part of the circle is okay until I get to here. And it's not okay because it's on that line. And then that goes like this. Now we want greater than 9 is okay as well. So that means things outside of this circle. So one way to do that is just shade the rest. So these are all good points over here, and these are all good points over here. Right? This is not allowed. The axis is not allowed. There's holes there, and nothing inside of the circle is allowed. But everything else that's shaded or on this boundary is good. That's a visualization of the domain, right? Now, I'd like to graph this in GeoGebra. What does it mean to graph? Well, it's going to stick every XY coordinate that it can and calculate that value and represent that value as a height. Right? So if I plug something in and I get it equals 1, then at that XY location, it's going to represent a height of 1. Right? And then I plug in another XY coordinate and I get another height somewhere else. And it connects all those heights together and will form a surface in three-dimensional space. That's what I mean by graphing this function. Let's see what GeoGebra can do here with this. Let me get this ready. Okay. Boom. All right. So we have our 3D. I turned on GeoGebra and then I clicked over here on the right and clicked on 3D graphics to get it into 3D graphics mode. And now all I have to do is go to the input down here and start typing in my function, right? So I can type in f parentheses x comma y parentheses equals square root of x squared plus y squared minus 9, close parentheses, divided by x. Ooh, that was a roller coaster. It was trying to graph as I went, but as I kept changing things, it said, oh, wait, that changes the shape. So take a look at what I can do here, right? This is what that function's graph looks like. And with GeoGebra, you can, of course, pick this up and move it and rotate it around and really observe the features of this graph, yeah? But one thing I want to first do is when I look above this graph, see what I see, right? See that? This is the x-axis, the red axis going out here. This is the y-axis, and I'm looking at it from above, right? And notice that what I get the picture very similar to the one I drew on paper. There's that circle where there's no output. There is no graph here, right? And remember that there's no output for the axis as well, right? Now, it's showing that there's no output for a lot of this, but that's because I'm zoomed in. If I zoom out, what's going to happen is that this is going to get closer and closer to that axis as GeoGebra fills that out more and more. Right? So when I zoom way out, you can see that this starts to approach that axis, right? So at the very least, it tries to show you a little bit of a picture of the domain. And so that is a kind of an interesting thing. The domain visualization here is basically looking at your graph from above and seeing what that looks like, right? So I'm seeing that it's not defined here, not defined there, not defined on this axis, and it's not defined inside of the circle, right? But then there we have the 3D picture of that, right? It's not perfectly represented, but of course it's doing the best it can, and it's really good for a free program, doing really well on that, right? Really cool features there. And it was really quick and easy to graph that without too much trouble at all. Awesome. Okay, let's do another one. Let's do another domain problem. So let's now look at this function. Let's see here. I'm going to pull one from the homework because they didn't really have a good one here. Let's see. Yeah, let's do a couple more of these. Like, so this, what's the domain of this function? What's the domain of f of xy equals e raised to the xy? Right? Okay, just like your regular old domain problems, right? You're just looking for pitfalls, things that are not defined, right? Things that you plug in that are problematic. Well, if you remember anything about the exponential function, you should remember that you can literally plug any number into it as its power. So it can be e raised to any power, and that's okay. Positive power, negative power, zero power, all good. So it comes down to, is x times y always defined? And of course it is, right? Your input, multiply them together, then take e raised to that number. This is all good. So what would be the domain here? The domain would be all xy. This would be, so the domain here would be literally all xy, such that x and y are real numbers. Now notice how that's a little different than saying all real numbers. All real numbers is a one-dimensional concept, right? Saying that you can pick any real number you like on this one-dimensional line. So you wouldn't really say all real numbers here, right? But you do have to communicate that you can pick any real number for x and any real number for y. Do you see that? So now that's the two-dimensional idea coming in. And if I was to draw this, this would simply just be the entire xy plane filled in. Every value is valid. Every value can be plugged in, and it would give me an output of e to that multiplication. Yeah. So that wasn't much to do with domain there. Okay. But I wanted to mention that just in case. All right. Let's try this one. Find the domain of this function. G of xy equaling y over the square root of x. So here we have the couple classic issues here. We're dividing, so we have to be careful with dividing by 0. And we have a square root again. So we want to make sure the thing is always positive or 0. But wait, I don't want or 0 because I'm dividing by it. So do you see, I better say that x needs to be strictly greater than 0. The square root gives me that x has to be greater than or equal to. But since I'm dividing, I don't even want the or equal to. Right? So I strictly get that x better be positive, strictly positive. Okay. So again, my domain here, all I would have to write is any xy coordinate where such that x is greater than 0, strictly. Okay. let's go ahead and graph these to see what they look like in GeoGebra. I'm going to look at the graph itself and then look from above to see if I can see what the domain looks like. Yeah. So I'm going to clear that fraction out, clear that function out. Didn't like that. It's like, what? I'm not ready. I'm not done with that. Okay, here we go. So here we go. This is going to be e raised to the x times y. See that? Right there. All right. Now, if I look from above, it's a little misleading. It seems like these numbers aren't allowed, and these numbers down here aren't allowed either. These XY coordinates don't seem to be allowed, but we got on a piece of paper that any XY combination is allowed. The reason it's not showing these from above is because the function is already higher than my max can show. This is only showing an output of 10. Think about what this is calculating. This is calculating e raised to the product. So that's going to be e raised to a big number right away, which of course is an astronomically huge number, right? And so the above trick, looking above trick, is not going to work very well because the surface climbs so fast. If I zoom out, it'll start to fill in more and more of this, but we're not going to be practically able to see this ever filled out because I already have to, this is already e to the 100. And e to the 100 is a ridiculously large number. So it's not going to fill in those until I like zoom way out, and it's getting worse. It's, yeah, not going to practically happen, right? And in fact, you start to see these weird artifacts. You start to see GeoGebra really struggling with because it's just working with ridiculously huge numbers or ridiculously small numbers. And so when you zoom out, it's trying. It does its best, but it's complicated. It's like, so anyway. Cool, okay. Let's graph the other one. The other one was y divided by square root of x. Y divided by square root of x. So here's the graph on that. Right, kind of a cool graph. Look at that, I like that. Looking at it from this way, looking at it down the y-axis, here's down the x-axis, here's straight up, right? And then rotate for the x-axis. Notice that I only have graph on the right-hand side. That's because x has to be greater than 0. There are no graphs pieces. There's no graph or surface pieces over when x is less than 0. So there's nothing here on the left-hand side. It's all on the right-hand side. Of course, again, we're running up against that height problem. So, but when I zoom out, you can see that the height problem tries to fix itself a little bit better, at least with this than it did with the exponential. So it's starting to fill in everything on this right-hand side. But still, it's, you know, it's hard because this goes infinitely large and infinitely small. All right, everyone. Hopefully that makes some sense, right? Doing the domain. First thing that we usually do when finding a function or when working with a function is trying to find its domain, right? What's valid to plug in. And noting that the domain is a set of numbers, of ordered pairs in this case, that can be safely plugged in. Okay, awesome. Let's talk more about this graphing thing here. Now, back in the day, of course, we would have to graph these by hand. Lots of things have changed since then. We now have free tools and we have expensive tools that can draw very professional quality pictures. And then we have GeoGebra that can do decent enough pictures for our purposes. So for instance, if I have the function of x and y, which is the square root of 16 minus 4x squared minus y squared, we have a function of two variables, right? I can now first, let's calculate the domain, see what's valid to plug in here. And then here they even ask us to find the range. Range is not always possible to find, or it's difficult to find. But for this one we can, and I'll show you a trick for that very soon here. And then after that, we'll describe what the graph is. And then we'll check on GeoGebra and see how good we were. Okay, so to find the domain, again, I have a square root of a bunch of junk. And so I know by our basic rules that that junk, no matter how ugly it is, I do know that this has to be greater than or equal to 0. Yeah. So that's a starting place, right? Now I'm trying to get this to look like something that I can work with, right? Is it a form like before we recognize, oh, look, it's a circle. It forms the equation of a circle. Is there something here that happens, right? So what I might want to do is let's subtract this and this to that side. Subtracting does not change the direction, right? Multiplying by a negative or dividing by a negative does, but subtracting does not. So this is still 16 greater than or equal to 4x squared plus y squared, right? And what I can do here is this is starting to look a little bit like maybe an ellipse, right? What I can do is let's swap it around. So this is 4x squared plus y squared. Now it's less than or equal to 16. And if this was an ellipse, I should be able to say that this is some x squared over a number plus y squared over a number equals 1. So if I want that to equal 1, let's divide everything by 16 to make that happen. And so I end up getting x squared over 4 plus y squared over 16 is less than or equal to 1. And indeed, this is an ellipse, right? Excuse me. So what we have here is that x really can only go between what? Negative 2 and 2. And here we have y can only go between negative 4 and 4. Right? So we have an ellipse. And in fact, that's what the edge is, right? This is equal to 1. That's the ellipse. And less than 1 are the points inside of that ellipse, right? So what I'm going to get here is a domain that looks very much like this, right? Graphing what this looks like. I have the x-axis, the y-axis. We know that x can only go between negative 2 and 2. Hopefully, does everyone see that, why that's true? Right? I mean, if this was 2, 2 squared is 4, 4 divided by 4 is 1, and now you have to add something, but you can't be bigger than 1. So when x is 2, you're already 1. So that makes that 0. You see that? So that means that the farthest out on the x-axis that this could go is negative 2 or 2. Here, same reasoning. The largest y could ever be is negative 4 or positive 4, because then this would be a 1, and so this would have to be a 0 to compensate. You understand? So that's what gets us the ellipse. This is 4, negative 4. Okay. Now, less than or equal to, so I can shade the inside. That's the domain of our function, right? Now, in fact, this should be a top view, right? This is going to be very nice of a top view. So I'm expecting my graph, when I look at it from above, to look like this ellipse, right? All right, so that's the domain. The domain will be xy's that obey this, or xy's that obey this, right? So if you wanted to write it down formally, you would say the set of all xy's such that x squared over 4 plus y squared over 16 is less than or equal to 1. That would be the formal way of writing the domain. Now they ask us for the range. Okay. Now the range is the outputs, right? Now I'm plugging in a two-dimensional point, an x and a y, so that's coming from a plane. I'm plugging in that point on a plane, and I'm getting a single number. So the range is going to be one-dimensional, right? Because it is the range of outputs that can happen, right? So let's think this through. Can you think of a minimum number that f could ever be? Well, for instance, if x was 2 and y was 0, notice what I get. If this was a 2, I would get 16 minus 16, which is square root of 0, and that's 0. So I can definitely get an output of 0, and because it's a square root, and I know that the output of square root is either positive or 0, I know that's the smallest output I could ever have. So I do understand, just looking at this formula, what the smallest output could ever be. The smallest output is 0. can't be negative because the square roots do not output negative numbers, right? The principal square root doesn't. Now the question is, what's the largest output that this could ever be? And there's a nice way to think of that in this one case. This doesn't always work for all functions, but for this one, I can do a little bit of analysis here. I can say, look, I have 16, take away 4 times x squared, so that's definitely taking something away, minus something positive, so taking more away. Do you see that the maximum this could ever be is take nothing away? Just start with the top. 16, take 0 away, take 0 away. 16 is the largest that this inside the square root could ever be, because these don't flip around to be negative, right? So that's an argument to say that this is the greatest value it could ever be, is the square root of 16, which is 4. And so the range of this function is from 0 to 4. So the range is from 0 to 4. There's not a good way to sort of have the math calculate that. You just have to look at your function and start thinking about what are the outputs available. And what's the smallest output you could ever have? What's the maximum output you could ever have? And that's why range is usually a tougher problem. And they won't ask you all the time for range. So when they do, you're going to look for something that you can easily argue what the maximum value is and what the minimum output is. All right, hopefully everyone's clear on that the range is an interval, because it's a one-dimensional idea, and the domain here is a two-dimensional idea. Okay, now that we have the domain and the range, we do have a certain sense of what this graph might look like, right? We do know, for instance, that the output, the smallest output would be 0, right? And so to get that, I would have to be on the edge of this ellipse, right? For instance, if I plug in 0, 4, 0, 4, 0, 4, notice I get square root of 0, which is 0. So this means that this is actually the base, the bottom of our graph. The bottom of our graph is this ellipse, right? And then to get this 4 as an output, notice that that's only going to happen in one single point. That only happens when this is the origin, putting a 0 here, putting a 0 there. So I get the maximum at the origin. And because of the way that this works, this is going to be elliptical as I climb. So this should look like an upside down elliptical bowl, right? With the wide ellipse at the base, and then the ellipse getting smaller and smaller and smaller till it comes to a single point at the origin. Now let's go to GeoGebra to either be proven wrong or to demonstrate that I am thinking of this correctly. Okay. So I'm going to say f of xy equals square root of 16 minus 4x squared minus y squared. Oh yeah, there you go. Look at this. There's the top view. Let's put the x-axis to the right. The x-axis is the red axis. So yep, that definitely looks like the domain. And then when I put this in proper standard sort of format with the x-axis coming out at us and the y-axis going to the right, z-axis going up top, we get, yep, that sort of upside down elliptical bowl. See that? That is what I was expecting. Nice. All right. So one thing that you want to do when you're working with this section is play around with GeoGebra, type the stuff in. I want you to see, visualize what these surfaces look like. Start to get a good feel for what the graphs of these things look like. That's kind of a nice habit to get into. Like, what does that look like? That's not an easy question all the time, but sometimes it is. Sometimes it's decently easy to do that. Okay. Now, speaking of pictures that are not easy to see, let's now get into other ways that we can look at the graphs of 3D surfaces. Okay. And this will actually bring us to something that you probably grew up with all the time. It was never presented as a 3D picture, which would be cool, but like a weather map, right? Have you ever seen those weather maps, which is like a temperature, right? And it gives you the color, like these are the 70s, these are the 80s, and these are the 90s, and these are the 50s, 40s, and 30s, right? And it would show you that weather map, right? What that's doing, right, is thinking of the United States as a flat surface, right? It's picking an XY coordinate, right? Maybe Chicago or something like that, right? Picking a certain location. And then at that location, a temperature is assigned to that location, right? And so what it does, right, what the computer's going to do then is coordinate all of the 70s that it got and put them in a certain color. Gather all the XY locations which have 80s degrees something, or 70 or 60 or 50 or 40, and make a color of it. What I'm interested in here are the boundaries, where the temperature is exactly 70, where the temperature is exactly 80, where the temperature is exactly 90. In other words, I'm not necessarily interested in the color between the lines. I'm interested in the lines themselves. We call those in math level curves. Level curves. And so let's define what I mean by that. And it's a way to visualize 3 dimensions without having to draw 3 dimensions. Okay, so we can use level curves, they're called. Sometimes they're called contour curves, right? And all this means is what do they say here? Yeah, the value of f of xy is constant. So these curves are the places where the value of the function, the output, is constant. So in my example, think about this. The xy are the locations on the map. And what that does is you plug that location into the map, and it calculates a temperature. Right? So this would be a temperature function of x and y. Right? Now collect all of the places on the map that have a constant temperature, like 70 degrees or 60 degrees or 50 degrees. And you would get something that looks like, let me pull this up, you would get something that looks like this. See here on the right, you would end up getting a picture like this, right? And so on this line here are all the places on the map that have reported 60 degrees. Yeah. On this curve right here, this is the curve where it's 50 degrees. Yeah. This is the curve where it's 40. This curve is 20, right? So the curve represents the position where the function is constant. In this case, since it's a temperature function, we don't call these level curves. Well, we do call them in math. We call them level curves. But in meteorology, we might call them isotherms. Same temperature, isotherms, right? And so we say that level curves show the lines of equal temperature, isotherms, measured in degrees Fahrenheit. Another application in level curves would be the following. Here's a map of the pressure measured in millibars, right? And so this is where the pressure is 1,008 millibars, 1,004 millibars, 1,000, 1,008, 16, 12, 1,008, 4, so on and so on, right? And since these lines represent where the pressure is the same, these are actually called in meteorology isobars. Isobars. And if you ever grew up watching Tom Skilling, he talks about isobars all the time. And so if you were interested in, like, any meteorologist that talks about this, if you're local, it used to be what, Eric Sorensen. And so yeah, he would talk about isobars all the time. And these are where the pressure, what the pressure is doing. Now, these are really nice because you can sort of tell when your pressure is increasing rapidly. Like, for instance, see how this line is 1,000 right here? And this line is 1,004, 1,008, 1,012. Do you see how that's quite a drastic increase? It goes from 1,000 to 1,012 in just the space of this much of this much length, right? Versus, like for instance here, this is going from 1,000, well, to 1,000. That's not much change at all, right? And yeah, so when these millibars, when these isobars are packed close, that's telling you that there's a more drastic change in pressure. So wait a minute, change, that's talking about a derivative, isn't it? So this contour plot actually is a way to look at how stuff changes. And you can tell that the change is quite extreme here and not as extreme here. See how these isobars are more spaced out? Yeah. And so there's not as quick of a change as there is over here with these tightly packed isobars. I think they have another picture here. Yeah. You could do elevation changes. Look at this picture, right? So this is like a topographical map, right? And you might have seen this. So instead of doing a three-dimensional map, right, that actually has the mountain into scale, what you're presented with is a flat picture, right? And those lines represent the heights, right? And so if you made me climb this mountain, which you would have to really, I mean, it would be a miracle to get me to climb a mountain. But with, with that being said, if I had to climb this, I'm definitely looking for the flattest part that I could work with, right? So in other words, I would not be climbing here, for instance. Do you see this? Look how packed these height bars are. See how the heights are changing? These bold ones look like they're like elevations of 50 feet maybe, or 100 feet, something like that. And so this is climbing quite rapidly if I was to walk this way, right? Now, if I was to walk along this curve, that would be a flat path. This would be the same height, right? So I would want to work like this if I had to go somewhere where the elevation change is not too brutal, right? But look at this right here. Look at this right here. Yeah. I mean, the climbing, the change, the isobars are not, they're not isobars anymore. They're, do they call them anything? No, they just the change of height is so quick there that I would not climb that. That is too steep, right? And so this is the idea of level curves. Level curves allow you to visualize a 3D thing onto a flat map, right? By representing the heights at various places by curves on that flat map, all right? Let's look at what we can do here on GeoGebra. I drew a thing. Let's see right here. Yes, 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 yes. Okay, let's try. I'm going to not start with a crazy complicated function. Let's start with a parabolic bowl like that. Okay. And I'm going to reset my view real quick. There we go. All right. So here's our default position, what I got going on. So here's what I want to do. I'm going to move this plane. See this plane? I get to control the height of this plane. And as it moves, it's going to cut the surface. It's going to intersect with the surface, right? Right now, the bowl is above the XY plane. And so this plane does not intersect with that bowl at all. So nothing is shown, right? In other words, there is no output to this surface that has an output of -6, right? There is no output of -4. There is no output of -2, but there is an output of 0. What it's hard to tell, but what this is doing is it intersected at this very small dot. At 0, 0, the output is 0. And so it drew a curve, which happens to just be a dot at the origin. Let's now, this is going to be a little bit more informative. Let's now move this plane up to c equals 2. Moving this up to c equals 2 has now intersected the surface with the z equals 2 and this surface here, producing a circle. That is the level curve for the output of 2. The next one here, this is the output for 4. This is the level curve for 4. This is the level curve for 6. This is the level curve for 8 and for 10, right? And so now I can graph a lot of these level curves together. When we do that, we call this a contour map, And it's basically just a drawing of all the possible, or not all the possible, but many of the level curves that I'm interested in, right? And so here, let's change this a little bit. So I can say, instead of just stopping at 10, let's increment by 1 and then maybe go to 20. Let's see if that can do that. Okay, so then I'm going to cut this back, and now here we go. So here I'm going to just draw the contour map of this. See that? Okay. So now what can we tell by this contour map? Suppose now you don't have the picture of the 3D graphics. Perhaps this is missing, right? You don't see this part. Boom, it's gone, right? And now all I'm given here is a contour map, right? You could probably still piece together what this looks like in a 3D sense, right? You say, okay, well, when the output is 0, I'm at the origin. Okay, so that's just a dot there. But now the outputs of 1 are this circle, and then the outputs of 2 are this circle. So as I keep climbing up on this shape, right, I'm getting wider and wider circles as I go higher and higher up. Now notice how in the beginning, these have quite a bit of space between them, right? But now as I reach higher outputs, do you see how they're more tightly packed together? That tells me that it's sort of increasing faster and faster, doesn't it? It's getting steeper and steeper. Here, it was pretty flat. And it slowly went from an output of 1 to 2, or 0 to 1. But the output from 1 to 2, it didn't take as far, did it? And the output from 2 to 3, not as far. Output from 3 to 4, 4 to 5, and so on. This is getting steeper and steeper and steeper. And so then you might guess or surmise what you end up getting here, and that you end up getting this 3D graphics picture like this. Yeah? See? Like that. All right, any questions with that? Are we doing okay with that? So you can get some crazy looking graphs here, right, using these level curves. We could do the hemisphere one that we just did. Let's go ahead and do that. We had, suppose my graph is, okay, I've got too many windows open, too much stuff going on. Okay, I'm going to change this now. I'm going to change this to, let's say, square root of 64 minus x squared minus y squared. Okay. All right. So I have this hemisphere, right? That's what this graph is looking like. And so now when I think of the level curves, I'm thinking about where is this thing equal to 0, yeah? And let me zoom out. I don't think I saw where it was equal to 0. Okay, here we go. I'm going to animate this. And what you're going to see here is that the plane is going to climb, 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 climb. And I'm going to graph the intersections, the level curves, over here on the left. Do you see that? And so that's what I end up getting. Now, these aren't perfect circles because of weird numerical problems with GeoGebra. Those are not mathematically happening, right? Yeah, these should be full circles, right? So there's some numerical error happening here, and it's not showing you the complete circle, but they should be circles. And here you can see that it's very steep around here. Like if I go here on the right, it's very steep here, but then it's not as steep here, and it seems to be flattening out here. And so I could see that corresponding to a shape that looks like this, right? Steep edges, either going up or down, and then a flatter top, either top or bottom. See, when you have just the contour map, it's hard to tell if you have elevation changes, right? Whether they're going down in elevation or are higher in elevation. But once you see this, you can definitely tell that that's the contour map associated with that. Okay. Awesome. All right. Let's see, what else? What else can we talk about with this? Oh yeah, let's do z equals y squared minus x squared. Now the reason I'm doing this in GeoGebra, right, is because it can graph things right away. Here's how I would have to do this on paper, right? I would have to say, okay, let me think about my outputs that I want, okay? And put them on a chart here, right? And then plug in and see what sort of equation that I get, right? So for instance, I might say, I want an output of 0. So I have to take this and I say, okay, set this equal to 0. That's the equation that I would have to graph. I would have to graph y squared minus x squared equals 0. Okay. Now, incidentally, this is maybe what you didn't expect. I could bring that over, take the square root of both sides, and I get that this is plus or minus x. In other words, when the output is 0, I get straight diagonal lines. So my level curves would be y equals x and y equals negative x. So if I live on this diagonal here, my output is 0. Right? Now I would go and say, okay, now I want an output of 1. Now I'd have to do the analysis all over again. I'd have to say, okay, start with y squared minus x squared equals 1. What type of shape do I get? Right? Now, this is actually a hyperbola. Right? So you can see quickly that doing these by hand is not the best because you then have to actually graph each one of these sort of manually, right? And start to recognize, oh, this is a hyperbola. This is a set of lines, right? And in fact, if I change this to a 2, I'm going to get y squared minus x squared equals 2. That's another hyperbola with different features. Okay, so you can see why I'm doing this with GeoGebra, right? Because to do a whole contour plot takes a lot of work to do that, because you're literally taking each level curve and sort of drawing it one at a time, right? But with GeoGebra, I can just say, you do it, right? And so here we go. Let's go ahead and I'm going to change this to be the function y squared minus x squared. Okay. I'm going to reset this. Yeah, it doesn't reset. I don't know in between. Oh, wow. It didn't even reset that. Hold on. It still has my last graph on there. Oops. Not sure how to get rid of that. Okay. Anyway, what I can do is now think about this plane intersecting with this weird purple curve, this weird purple surface, right? And I'm going to look at its contour map that it's drawing out over here. Remember we said we'd get hyperbolas? And indeed we do. And look at that. All right, let me zoom in here so I can see what's going on. Right, so remember, every one of these lines represents an output. So if I said, I wonder if I plug in this point here that I'm plugging in right there, see where I'm pointing right there? That would be an output of 5. I don't know where that is xy on this map, but I do know if I plug it into the function, I get an output of 5. There's 4, 3, 2, 1, and 0 should be the straight lines, remember? Boom. Right? So what I'm seeing is that the flattest part, if there is such a thing as a flat part on this graph, is like around here. And then it starts to climb pretty steeply or drop pretty steeply. And in fact, here, these are so packed, I can't even tell the difference between the bars, right? So this is a precipitous drop or a climb, right? This is ridiculously large change there. Okay. All right, so these contour plots can help you visualize what's going on here, 3D pictures, and all that good stuff. Okay, let me zoom out and see what we got here. Show you other pictures here. Yeah, look at these, right? So they've graphed these with the computer technology they had at the time. And so, yeah, we got these pictures here. These look pretty good. These are like wireframe pictures of these. And so here's 3 different views of this graph, right? I would go ahead and type that into GeoGebra if I were you and see what you got, right? And what they've done here is you can say single traces, right? And here they've done double traces, and here they've done level curves. If you were to look at this from above, this sort of graph, you would see sort of this change in height like this, right? And just other demonstrations of pictures and things you would get. We have GeoGebra now that you could be able to play around with this a little bit with that. Let me get into this homework thing, what they got here. Yeah. Where is it? Where is it? Yeah, so for instance, take a look at these. We have contour maps, and they're trying to match these to what sort of shape, what sort of graph I would expect. Yeah. So take a look at these graphs here. We have these 4 contours like that, and we have these 4 pictures here. We have this one, we have this one, and then sorry it's not on the same level, but we have this one and this one. So the point is, well, can I tell from the contour plot which one of these contour plots goes with its graph, right? So like for instance, I'm looking at this one, right? Notice how the output here is pretty low, right? The output is not very tall at all around here. And it slowly grows, and then near the origin, it changes height rapidly. And thinking about the top view of this, I could foresee it being circular if I was to cut this at different heights. So I hope you would agree that it looks like C right here, this contour map, would go with this picture here, right? And that's because it starts off pretty flat like this over here, and then it climbs pretty quickly and then comes to a peak, sort of a, just a peak spot there, and then, falls down again and then flattens out as it goes. So I would match C with this one here, right? See if there's another one we can knock out pretty easily. Yeah, look at this one here. So see this? This I know has to be ellipses, right? So it's sort of like, it's like oscillating with ellipses, right? If I was to look at this above. And so I'm looking at this picture here, right? To do that. Now, what's curious here, right, is that these, I can't tell if it's just doing this nice like this, or if it is oscillating. See how I lose that information when I'm looking at a contour map. All of this contour map is going to do is say that on this curve, the output is the same. I don't know if that output is more or less than what it was, right? Without labels. And this one's not labeled. So your guess is as good as mine. If I was just to look at that, I would probably assume it was like a dome, right? It was a dome, but it's actually not a dome. It actually is like a dome, except it oscillates. So those heights are changing, yes, but it's not quite picked up by the contour map, yeah? So sometimes it's really tough to match up a contour map with its graph, right? But I'd like you to practice at least a little bit. I'd like you to look at GeoGebra and start to really get into that idea there, right? So things you should be able to do in your homework here, right? First off, you can skip these. Determining whether an equation is a function. All you're trying to do there is, do you get a single answer for z when you plug in a single answer for x, y? I'm moving on from that. But here, get your feet wet with evaluating functions by plugging in values. Just getting your feet wet with working with multivariable functions. So these are literally just plug in, calculate your values. So just practice that. And then finding domain. And here they're also finding the range. So these are all possible to figure out the outputs in some way. The argument might be a little different each time, but that would be problems that you can actually find the range. So I would focus on those as well. And then focus on working with practicing surfaces. Now they say to sketch a surface. I don't know if I'd sketch it on paper, although we are going to have to draw stuff on paper later. So if you want to start practicing that now, be my guest. That would be good. But of course, you can always use GeoGebra to graph these, right? And see what you would get, what it would look like. And in fact, these are specially made for technology. And so these would be really nice to look at in GeoGebra. So I would ask you to do that, play around with that, look at those graphs, and then see if you can look at contour maps. Now, I did not share this level curves thing. Maybe I should do that. Maybe I should share this GeoGebra thing that I made, right? It's not very user friendly. You just have to change your function here by double clicking, and then you would change your function, right? So square root of 16 minus x squared minus y squared. Change that. And then it's a little goofy. Yeah, look at this. It doesn't clear it very well. Let's do this. Let's see. What if I turn off the view and turn it back on? That fixes everything, right? Yeah, it actually did. Nice. So anyway, I might share this so you can look at level curves as well, right? And so chopping this at different heights and then seeing what that looks like here, right? And then you can look at the contour maps with GeoGebra. All right, with that being said, I think that does it for this section. Yeah. So I think I'll leave it there. The next section, we're going to start talking about limits of multivariable functions. We want to see, now that we have functions, we're going to start that whole process of calculus again. We're going to be like, well, we have functions now. What do? We did domain range. Now we're going to ask, well, what does it mean to take a limit of a function, multivariable function? Is that the same as Calc 1? Are there ideas we can borrow from Calc 1 that change when we're talking about multivariables instead of just a single variable? Then after limits, we're going to be asking, well, what about derivatives? What does it mean to measure the rate of change of a surface, not just a function graph, but now a whole three-dimensional surface? How is that 3D surface changing? That's a very basic fundamental question we want to ask in calculus, right? And so we have to develop some idea of derivative of a multivariable function. And we're going to find that that's not super easy to do, that there's a little bit more work that has to go into that because there's more independent variables around. And so that means much more chances, many more chances for change to occur. Yeah? And then not in this chapter, but in the next chapter, we're going to start asking, what does it mean to integrate multivariable functions? What does that do? I mean, the integral in Calc 1 gave us the area under a curve. I wonder if I integrate a multivariable function, does that get me like the next step up? So instead of area under a curve, do I get volume under a surface? And the answer is actually yes. Yes, you do. So that's the path that we're going into the second half of this course. Yeah, we've actually gone through the first half of this course, haven't we? Being midterm this week, yeah? So anyway, that's where we're headed in this second half, all right? Exciting stuff, good stuff, useful stuff for lots of engineering, and I'm reading a thing on space dynamics right now, and the whole book is Calc 3. Just the whole book is like everything we do is based off of multivariable functions. And so it's showing up everywhere in the stuff that I'm interested in as well. So someone's using this stuff, might as well be us, yeah? All right, everyone. Hope you're doing well, staying healthy and happy. Looking forward to checking in with you on Thursday. And until then, be well. See ya.